This is a tutorial on exponential growth and decay. The first thing that we're going to talk about in this tutorial is exponential growth. And to demonstrate exponential growth, we're going to use uninhibited population growth models. Here is our model for uninhibited population growth. We have P of t, or the population at time t, is equal to P naught, or P with this zero subscript. This means the population at time 0, or you can think of that as our initial population, or our starting population. And this is multiplied by E, our natural constant, to the kt power, where k is our growth constant. This is the number that determines how fast we're going to grow. Now k has to be positive if this is going to be an exponential growth. So let's look at an example. A bacteria colony is experiencing rapid and uninhibited growth. There are initially 20 cells of bacteria in the colony, and then after 1 hour the colony is made up of 120 cells. So how large will the colony be after 12 hours? Well, let's think about what we know here. We have our equation. P of t is equal to P naught times E to the kt. We know our initial population. That's 20 cells. We don't know k, but we do know that the population at, say, time 1 hour, that's equal to 120. And we're asked to find the population after 12 hours. Well, let's use this information, because if I plug this in, I'll have both this and that, and our P naught, and all I need is k then, or I can solve for k then. Because the population at time 1, that's 120. And this should be equal to our initial population, 20, times e to the k t, but in this case this is at time 1, so plug in 1 for t. So I have 120 is equal to 20 times e to the k. Now this is an exponential equation with my variable in the exponent, so if I want to solve this, I have to get this exponential term, or this e to the k term, alone. So I'm going to divide both sides by 20. I'm going to end up with 6 is equal to e to the 1 times k, or e to the k. So here I have my exponential isolated now on one side of the equal sign, and it's equal to some number. So if I want to get this k out of the exponent, I have to rewrite this as a logarithmic equation. Now since I have a base e, I'm going to write it as a natural log. This expression here is exactly the same as saying that the natural log of 6 is equal to k. Well, if you plug in natural log of 6 into your calculator, k is equal to approximately 1.792. So I found my k value for this bacteria colony, and I can use that to find my population at time 12. I just plug all this stuff back into this equation. I'm looking for P of 12, or the population at time 12. This is equal to our initial population, which is 20, times e to our k value, which we just found, 1.792, times our time, well, we're looking for the population at time 12, so times 12. If you multiply 1.792 times 12, you'll get approximately 21.5. Now this is the exponent of e and still multiplied by 20. E to the 21.5 power, that's a very large number. This is 2,776,782,336. And this is still multiplied by 20. If you multiply that by 20, you're going to find out that after 12 hours, the population of bacteria is 43 535,646,720. So there are over 43 billion bacteria cells in the colony after 12 hours. So now that we've looked at exponential growth, let's talk about exponential decay. And to demonstrate exponential decay, we're going to use radioactive decay. The formula for a radioactive decay is that the amount of material at time t is equal to the initial amount of material, A0, times e to the kt. Notice that this is exactly the same formula as we had before. The difference, or the reason why this is a decay, is that k here, our decay constant, this is going to end up being negative. But otherwise, this is exactly the same equation. So now let's look at an example. One of the byproducts of nuclear power generation is uranium-233. Uranium has a half-life of 159,200 years. That means if I have a quantity of uranium-233, half of it will decay in 159,200 years. So if 120 pounds are produced from a power plant, how long before it degrades to less than 1 pound? Well, let's think about what we know. We have our equation. The amount of radioactive material we have at time t is equal to the initial amount of material times e to the kt. Our initial amount here, that's equal to 120 pounds. We have our half-life here, but that's not our K value. But I can say that the amount of material after 159,200 years would be half of our initial amount. So if my initial amount is 120, half of that is 60. And what we're looking for is the time, or the t value, where we have less than 1 pound left. Well, let's just solve that for when we have 1 pound left. So we have basically all the same information we had before. I'm going to plug in my initial amount into this equation. I'm also going to plug in this value for time and this value for AT, and then I'm going to solve for K. Once I have my K value, I'm going to plug in this amount for A sub t, or AT, and I'm going to solve for T, because that's what I need to know. I need to know the time when we have less than 1 pound, or let's just say 1 pound. So first step, plug everything in. 60 is equal to my initial amount, 120, times e to the k value, which I do not know, where that k value is multiplied by 159,200. Because I'll have 60 pounds of this material after 1 half-life, or after 159,200 years. Here again, I have an exponential equation with my variable in the exponent, so I'm going to have to isolate this exponential term, or this e term. I'm going to divide everything by 120. So I'm going to end up with 1/2 is equal to e to the 159,200 times k power. I'm going to rewrite this as a logarithmic equation, so the natural log of 1/2 is equal to 159,200 times k. And then I'm going to divide everything by 159,200. And that means k is equal to the natural log of 1/2 divided by 159,200. If you plug this into a calculator, you're going to find k is a very small value. K is a negative 0.0000043 435. But I have my K value, so I can now use that to find the time it takes to get this down to 1 pound. I go back to my initial equation. This time, AT is 1. This is equal to my initial amount, which is 120, times E to the K value of negative 0.000000435 times T, because T is what I'm solving for in this equation. Now I have the same steps to solve. I need to isolate my exponential term because my variable is in the exponent. So I'm going to divide both sides by 120. So I'm going to have 1/120th is equal to e to the negative 0.000000435 times t. Write this as a natural log equation. So the natural log of 1 over 120 is equal to negative 0.0000435 times t. Divide both sides by this negative decimal, and you'll have t is equal to the natural log of 1 over 120 divided by negative 0.000000435. Put this into your calculator. T will be equal to 1,100,572.8 years. So it will take over 1,000,000 years for 120 pounds of this nuclear waste to degrade to less than 1 pound. Another common application of an exponential growth or decay is Newton's law of cooling. And here we have the equation of Newton's law of cooling. The temperature at time t is equal to the temperature of the environment plus the initial temperature of our object, whatever we're talking about, minus the temperature of the environment times e to the kt. So temperature at time t, that's the temperature of our object. The temperature of the environment is the temperature of, you can think of the outside or the area surrounding our object. T naught, or T with this 0 subscript, this is the initial temperature of our object. K is our cooling constant, how quickly or how rapidly this object will cool, and then T is time. So now let's look at an example of Newton's law of cooling. A 12-ounce can of cola is at room temperature of 75 degrees Fahrenheit. If you place the can in a 28-degree freezer, how long before it gets to the ideal drinking temperature of 34 degrees? And we're told that K is equal to -6 if T is in hours. Well, we have to go back to our equation where the temperature of our object at time t is equal to the temperature of the outside environment plus the temperature of our object minus, or the initial temperature of our object, minus the temperature of our environment times e to the kt. We know that the temperature of our object initially, or T naught, that's equal to 75 degrees, because our can of cola is at 75 degrees to start with. The temperature of the environment, well, we're putting this into a 28-degree freezer, so the temperature of our environment, that's equal to 28 degrees, or just 28. We know our K value, that's equal to -6, and we want to know the time t is equal to some number when our cola is at 34 degrees. Well, let's plug in all the information we can. 34 is equal to the temperature of our environment, which is 28, plus the initial temperature of our object, 75, minus 28, times e, the natural constant, to the negative 6t power. So what I need to know is in the exponent of this exponential term, this e term. So I'm going to have to get this alone on one side of the equal sign. I'm going to subtract 28 from both sides and end up with 6 is equal to, now 75 minus 28, that's equal to 47. So I have 47 times e to the negative 6t. Divide both sides by 47. This doesn't reduce, so I'm going to leave it as it is. I'm going to say that 6/47 is equal to e to the negative 6t. I have my exponential alone on one side of the equal sign, so I'm going to rewrite this as a logarithmic equation to get this variable out of the exponent. If I do that, I'll have that the natural log of 6/47 is equal to negative 6t. Now I just divide both sides by negative 6, and I get t is equal to the natural log of 6/47 divided by negative 6. If you plug all this into a calculator, you'll find that t is equal to approximately 0.343. Now remember, this k value is if t is in hours, so this is 0.343 hours. And that would be our solution. If you're curious what 0.343 hours is, you can multiply this by 60, because there's 60 minutes in an hour, and that would come out to be about 20.6. So it would take about 20.6 or 20 and a half minutes to cool your cola down to 34 degrees. Now the last type of exponential growth or decay models that we're going to talk about are logistic growth models. Here we have the equation for a logistic growth model. This is the basic form of this equation. The population of whatever we're talking about at time t is equal to c over 1 plus a e to the negative bt. Now a, b, and c are all constant values, but c is going to be the maximum value. Notice, as this denominator gets very large, this whole fraction here will get very small. If we went the other way with this, though, if this term got very small, you'd be adding a very small number to 1, and this essentially would just be c over 1. So the way that this equation is set up, c is the maximum possible value. This is the biggest your population can get. B is your growth or decay constant, and since we have this negative out front, even though this is in the denominator, if b is greater than 0, then this is going to be a growth model. If b turns out to be negative, you'll have a negative times a negative, and this will become positive, but again, because this is in the denominator, this becomes a decay model if b is negative. As you can see, logistic growth models are very complicated. There's many different constant values that incorporate into making this model. So rarely will you ever be forced to solve for these constant values, a, b, and c. Logistic growth models are important, though, because they model actual behavior in real life. If you have a logistic growth model, its graph will look something like this. Notice at the early times, or at the beginning of our time scale t, this looks like an exponential growth, or an uninhibited exponential growth. Once you hit the halfway point, this turns into a logistic graph. And as time t continues towards infinity, this line will approach the maximum value of c, but it'll never actually hit it. This maximum value of c is just an asymptote. Logistic decay models operate the same way, except they're just inverted. Here we start very close to our maximum population. Then we decay like a exponential, and then we turn it into the inverse of a logarithmic, where as t goes to infinity, we approach 0, but we never actually hit it. These models are typically used for populations that have a cap, or a limit to how big the population can grow. So now let's look at an example. Here we're told that the population of squirrels per acre in the Grand Canyon National Park can be described using the logistic growth model. Population at time t is equal to 2 over 1 plus 0.5 e to the negative 0.04 t. If the kaibab squirrel was reintroduced to the forest 10 years ago, what is the population today? Well, looking at this model, P of t is equal to 2 over 1 plus 0.5 e to the negative 0.04 t. This 2 value up top here, this is my c value, and 2 would be the maximum population. So whatever answer I get has to be less than 2. 0.5 is one of my constants. This is the a constant. And then 0.04, which is negative, or has the negative in front of it, this is my b value. Now because this negative is out front of it, that means I have a positive b value, where my b is equal to 0.04. So this is going to be a growth model, because this is positive. Now if I want to solve for the population of squirrels per acre, all I do is plug in 10 for t. If I do that, the population after 10 years is equal to 2 over 1 plus 0.5 times e to the negative 0.04 times 10. If we simplify this a little bit, this is equal to 2 over 1 plus 0.5 e to the, well, negative 0.4 times 10 would be negative 0.4. So I just lost a 0. E to the negative 0.4. This is equal to about 0.67. So I have 2 over 1 plus 0.5 times 0.67. 0.5 times 0.67 is about 0.335, so this is 1 plus 0.335 over 2, or 2 over 1.335. And if you solve that, this comes out to be approximately 1.5. So after 10 years, there are approximately 1.5 squirrels per acre in the Grand Canyon National Park. So that's an introduction to logistic growth models, and that's how you can use them to solve. And that completes the tutorial on exponential growth and decay.